And it's about 5 times what the MER was. And I mean, almost an order of a magnitude bigger than Sojourner from Pathfinder. So this thing is huge. So, of course, entry, descent, and landing. I'm not sure if some of you have seen this video called 7 Minutes of Terror. It was put out by JPL, and it's a great video describing the thrill and a little bit of insanity that we had to have to be able to design this and actually do this entry, descent, and landing for MSL. Entry, descent, and landing is very difficult. You actually can't test from end to end at Earth the entry, descent, and landing design. It has to be tested in pieces. So the first time that you fly this, for the first time, is at Mars. And actually, MSL was going on about the same time as the Olympics. And we thought of a good analogy. It's like you train your whole life, you test and you analyze and you get everything, all your ducks in a row, and you have that one chance, like an athlete training for a race, you have that one chance to get the gold. We had one chance to get it right. It was either going to be wrong or right. And past experience, we landed 6 successful landers, had six successful landings on Mars, and now we have a 7th. And Curiosity landed at Gale Crater, which is pretty equatorial. And so now our success rate actually for landing missions at Mars is about 88%. So it's great, but it requires a lot of work. The entry, descent, and landing sequence for MSL was very complex. There were a lot of things that we were doing that were new. So to take you through this, because I have a video next, to take you through this, of course we start at the top of the atmosphere, and for MSL we were going almost 6 kilometers a second, about 13,000 or so miles an hour. And we had to decelerate, and we actually used for the first time an active entry guidance, which was based off of Apollo, actually. And so we went through what we call a range control phase, just to talk a little briefly about it, because you'll see this in the video. We administered bank reversals, where we basically modulated our lift vector, controlling our lift to drag, to be able to minimize the errors in our downrange to the target. So that was what we did for the range control phase. Then we switched to this heading alignment phase. And the heading alignment phase, it said, all right, I am where I am, and now I need to manage or reduce the errors that I see in my out of plane position. So your cross ranger. So it just kind of hones in then on the target until we get to parachute deploy. Now for MSL, we deployed the parachute at Mach 1.7, so it's 1.7 times the speed of sound, just over 400 meters a second, at about 12 kilometers above the ground. And again, like I said, it was the largest parachute we've sent to Mars, and so far what we're seeing, it performed very well. And there's actually a picture, you can Google it or go on some websites I have that I can give you later. They took a parachute, a picture of the parachute, MSL on the parachute, the high-rise image from Mars Reconnaissance Orbiter. They actually captured it on shoot, which was absolutely incredible. So we have parachute deploy, and then of course we have to get rid of that heat shield that protected us during entry. So we jettison that about almost 10 kilometers above the surface. And then, of course, we have to get the rover out of that back shell somehow and separate from the parachute, because after a while it's really no good to us anymore. So that's back shell separation that we call that, and that was just over about 1.5 kilometers above the ground. And these numbers that I'm spouting off to you, these are actually the design, the nominal, as we call it, numbers that were actually very close to what we're finding we actually flew. So, so far with what we're finding for reconstruction, we call it trajectory reconstruction, things are looking very good, they look very nominal. So we separate from the back shell, and we have this powered descent vehicle, which has a descent stage and a descent stage attached. The rover is attached underneath, and that descent stage has 8 Mars lander engines that powers it down to the surface. So we go through a powered descent phase, and then we get to sky crane. And sky crane, I'm actually going to try to set the mic down and do this. I'll talk really loud. But sky cranes, basically, you probably have seen before, the descent stage comes down, engines firing, and we actually throttle down to, using 4 engines about 20 meters above the surface. And then we lower the rover on these suspension lines, basically, about 9 meters long, and it descends to the surface like this. There's a touchdown trigger where the descent stage senses that the rover has touched down, and it cuts the bridles, has these pyros that cut these 3 bridles, and it flies away. And the descent stage flies away with reserved propellant to a location at least as far away from the rover. And actually, we were finding it flew really, really far. We had a lot of propellant. So this is basically the entry, descent, and landing breakdown. And I'm sure some of you have seen the 7 Minutes of Terror. This video is not 7 Minutes of Terror. The video that I'm going to show, it needs a little intro, is Google Mars. Google Mars has actually worked with us at NASA Langley Research Center, which is where I work. And we have an entry, descent, and landing simulation. That's actually what I had worked on, the flight mechanics simulation. For MSL, we were the primary simulation. So we actually used Google Mars for a visual of our trajectory to be able to see what was going on and get kind of a panoramic view of the landing site. And you can kind of actually feel the bank reversals. And we used it for not only education purposes, but for our own uses. And this video that I'm going to show actually is based off of telemetry that was on board. There's no numbers or anything, there's no data that you're going to see flash on the screen, but it's going to take you through the entry, descent, and landing. And because entry is pretty long and I don't have much time, we sped it up to about 8 times real time. So I hope this isn't like a Japanese animation, you guys don't get sick, because it's a little bit of a roller coaster, but it's actually kind of fun. So who's ever working in the back, if you could click on the video. I wish we could turn off the lights. So Google Mars, actually, this is going to be, there's a version of this already in Google Mars right now. We've been working with them, so you can go down and download it if you have Google Mars already. That's great, and you can take this trajectory tour. So you'll see the events pop up. Guidance start is when we start feeling the appreciable Mars atmosphere. The bank reversals, I mean, this is the full bank reversal, of course, 8 times real time. And then when we get to parachute deploy, it's going to slow down to real time. So we just went through heading alignment, so you can see you're honing in on the target. And what you're going to see next is these entry balance mass jettisons. And what happened was we had to get the vehicle from an angle of attack, because we flew with lift, to 0 angle of attack before we deployed the parachute. So we actually deployed these tungsten, they weren't actually balls, they were like these cylindrical shaped tungsten masses that we ejected one by one to get us to 0 angle of attack, or to get, so that has already happened. We've just deployed the parachute, and you can see sort of this swivel rocking motion of the capsule. And that's actually, the capsule actually experienced these large attitude rates and would oscillate while on the parachute, because this parachute is huge and it has a large effect on the capsule. We have an overlay image. This is, these are the Marty images that you may have seen or seen the video from that overlaid. And so it's kind of neat because you can see the same picture in Google Mars. We've already gone through radar lockup, which actually happened a lot earlier than what we'd expect, and that's a good thing. The Marty images are kind of popping up, so you can see the same terrain features in Google Mars that we saw in the Marty images, which is kind of neat. And when we separate from the back shell, if you remember, because we have to get that powered descent vehicle out away from the parachute, we go through a divert phase where we want to get away from that parachute. We don't want to be anywhere near that parachute, so we don't have any recontact or anything like that. So we've gone through that, and now we're descending onto the surface, and we have yet to find a way to really show the plumes of the rockets in Google Mars, but we'll probably figure out a way. And Google Mars this is our actual landing location in Google Mars, so you'll see that right now, and you'll see a version of this video if you guys download Google Mars. Here we separate from the back shell, so now we enter that powered descent phase, and you can see at this divert, we're kind of off at an angle, and we divert from that parachute back shell system to get away from that. And so keep in mind, again, this is real time. And my heart was, I was actually at, not in mission control, the building next to it, in what we call the war room. My heart was pounding. We were actually watching data coming back from the rover on VOCA, and we had to relay information to mission control. And I'm going to talk a little bit about that in the next slide. And then here we have sky crane, where we separate from the descent stage. The rover separates down and touches down on the surface. And then the bridle lines are cut away, and the descent stage flies away to a safe distance. Now, the neat thing in Google Mars, and I couldn't really do here, was we overlaid the audio from that night, and you can hear all our voices. We overlaid the audio, and that plays in the Google Mars tour. So it's really, it's just every time I watch it, it just brings chills. And so this is kind of a panorama of the landing site, and you'll see our landing dispersion ellipse here. And that was the actual touchdown location. There's the thingy. So when that thing was coming down, we actually prepared, and we were there in the war room and mission control hours before entry. And we had to determine, as we were getting data back from Curiosity, we had to determine once we knew the rover had touched down, we had to understand, was it safe? Are things looking nominal? And so there was a 3-step process I want to take you through, because it was, at least so far, the highlight of my career. Step 1, I was able to call out on VOCA to mission control, and this is all public information, so you can go on YouTube and listen. There's all these renditions of the audio that night. And we had to know, were the touchdown velocities of the rover nominal? But I couldn't say touchdown, because then you'd have people that are like, oh my God, we touched down. And that was only step 1 out of step 3, or step 1 out of 3. And so we came up with a code, and it's actually kind of gone viral. People are like making jokes when their planes touch down. They're like, Tango Delta nominal. But Tango Delta is just TD for touchdown. And nominal is, yeah, it looked good. The touchdown velocities were awesome. And so that actually came back on my computer screen, and it felt like hours that I finally got out Tango Delta nominal. And that was just absolutely incredible. And knowing that data that's coming back is coming back from the rover. It's not, these operational readiness tests where we practice it. It was real. It was so real. Then the second step was RIMU stable, which basically just meant the rover isn't sliding down a slope, attitude looks good, things are looking good. So that was RIMU stable. That was a coworker, Dave Wade, that said that. And then step 3, UHF is good. All that meant was we were getting descent stage data back from the descent stage, so it was flying away. It wasn't sitting on top of the rover, which would have been a bad day. So UHF was good. That was Brian Stratz, and that was the 3rd step. And then Adam Stelzner hits Al Chan on the shoulder, and he says, touchdown confirmed, and everyone screams. I wish I had the audio. It would be a lot cooler. So that was kind of just what happened there. And then you kind of step back and you look at it, and you look at all the previous missions. I showed you that touchdown ellipse, and where we thought we would have landed, the dispersions on that. And Curiosity, because we have entry guidance, so we have improvements in navigation, we had all these improvements for Curiosity. If you look at that compared to other missions, it is way more precise than the previous missions. So these are kind of the advancements that we're going to be making, because soon that ellipse is going to be too big. So that was kind of a great thing about MSL, and we can learn from that. So Curiosity is on the surface, it's doing well, and this is the most awesome self-portrait ever. High resolution, you can download it, taken by the Molly camera. And it's making discoveries, and we're on Sol 93, I think, today, and things are looking good. So I have information, websites. I don't know if you can actually scan it. The QR code is probably small, but I have a printout of that. You guys can scan it and find me afterwards. So thank you.
Thank you, that's great. Is this on? Yep. Hi, I'm going to talk rather boldly about a new goal for NASA. I work at the Harvard-Smithsonian Center for Astrophysics. This is not endorsed by either of my employees. I'm employers. I'm on my own dime here. And let's see. Okay, I feel cheated because when I was in high school, this movie came out, and I thought that was an entirely plausible future for me. I could be up there on the space station, on a big space station, having a great time and going to space myself, right? And it's not happened. And the problem is NASA's budget is much too small. We all agree with that, but it's much too small. It's orders of magnitude too small. The entire space industry on the planet Earth is smaller than Walmart, so the whole industry is too small, right? What do we want? We want an exponentiating space economy, not something that stays more or less the same size over decades. We want something that grows by factors of a few every few years. Why do we want it? Because we want a human presence throughout the solar system. The next destination is the entire solar system, because we want a safer, richer Earth, and we want science breakthroughs. The only way to achieve that is through commerce. Greed is the counterweight to caution, I like to say, because the profit motive gives us a big incentive to bring down costs. Agencies and the government is always looking to reduce risk. That's very important. You don't want people dying left and right, but there's no countervailing force. We need commercial space ventures, and we're just starting, where the government is not the customer, because the government is a monopsonist. Look that up. If we have that, we get unlimited growth, and that's what we need. So the government's not the answer, but the government can help, as it has historically in the US, and I'm going to get to that. The most important thing to do when you're the government is to set a clear goal. The right goal. And President Kennedy did that very effectively. I'm stuck now with this thing. Which one is the one? Oh, ha. No. Well, now we're stuck. Oh, I know what's wrong. It's because I'm looking at my screen, not yours. Where am I? I can't see. Well, it was worth seeing again. That's what's wrong. Okay, my apologies. I give up on my screen. Choose the right goal. President Kennedy's goal was very clear: put a man on the moon and bring him safely back to Earth before this decade is out. That was great because clarity organizes your goals, right? You give those very talented engineers at NASA a very clear goal, they will achieve it because they are extremely talented, as we have heard. The problem is, it's a self-limiting goal, this one. This is game over once you've been to the moon, and that's been our problem, right? What we now have is a better goal from that point of view, which is developing the flexible path, which is developing technologies which will sometime enable us to go to the asteroids, to the moon, and to Mars eventually. So it's great because it's ongoing, it's open-ended, but it's vague. It doesn't define a program as crisply and cleanly as a true engineer needs in order to get the job done, not like the moon landing. Instead, I'm going to propose this, that the new NASA goal should be to enable the commercial development of space resources. It is not exploration. This is the exploration side I'm talking about of NASA, not the science side. But human exploration is not the goal. It's a consequence of doing this, developing commercial exploration. That will enable, first of all, it defines a very crisp and clear program, just like the moon landing. Second, it's ongoing, open-ended. Third, when you start looking at it, and I'll give you a few examples, it really enables much more interesting human exploration than we've had to date in the last few decades. And it makes NASA's budget seem like an investment, not entertainment, which is more or less what it is nowadays. It's inspirational entertainment, that's great, but once you turn it into an investment in the economy, then resource extraction industries get much bigger subsidies from the government than the NASA exploration budget, and we will be able to have a bigger exploration budget because we're doing something that's economically valuable. Now, the big question with all of this commercial space stuff is, What's the first thing you do? It's great if you had a operating space economy, there'd be plenty of things that would make a profit in space. But the problem is, there's nothing that makes a profit right here on Earth. So the important first message is get real about this, right? There are all sorts of things talked about. Mining helium-3 for fusion reactors from the moon's surface, wonderful, but which fusion reactor do you have in mind to put it in? We haven't got one, and we're not going to have one for decades. This is not short-term. Space solar power is absurdly expensive and overwhelming and impractical. As the sage of Princeton, Freeman Dyson, says, those people do know that the sunlight comes to Earth for free, don't they? You've got a big cost problem to overcome that. So the other possibility that's obvious, there is the moon, is water from asteroids. I don't think that's a good market either. I looked into it. It's not going to work in the short term. It will when we have a space economy, because that's a great way to get propellant and life support in space when we have a space economy, but we don't have one yet. The only thing I've found, and that people have talked about, are precious metals from the asteroids. The problem is, fundamental problem in space, no one can hear you sell. You've got to have a customer on the ground, because otherwise your vast resources are worth nothing, right? So, platinum mining is a possibility. If you take the right asteroid, 200 meters in diameter, it contains about $30 billion worth of platinum. So that's a promising amount of money that might interest venture capitalists. But those asteroids are not easy to find. That's why my astronomer's hat comes in. I left my hat in my hotel room. It's a good hat. It's a brown hat, though, because I'm not a lunar guy. So. Okay? The great thing is, once you say, okay, we're going to concentrate on what the first thing that will make money is, it defines a program. You've got to find these things, you've got to prospect them, you've got to learn how to mine them, and you've got to legalize the whole process. And to appeal to Congress people, don't forget, in the end, you will tax this. So this is good. Let's give a couple of examples. The space station famously is an engineering marvel, but doesn't really do any very exciting science. Maybe that's premature of me, but I suspect not. I think this gives us a great thing we can do. We can take up asteroid simulants, a few kilograms of rock, put it on this Kibo exposed platform, the Japanese module, which has the largest amount of volume and power available, and test mining techniques in a small way in the vacuum and low gravity of space, which is very similar to asteroidal work and very dissimilar to mining on Earth. The two cultures of mining engineering and space engineering will hate each other for a long time because you have very different priorities, but you've got to get along. And then, a great thing I was study I was on at Caltech last year is the next thing you do is bring a small asteroid back from solar orbit. This is not even solar system engineering 101. This is kindergarten solar system engineering, just proving you can color inside the lines, right? It's about 10 meters or so across. You can bring that back in a few years with 30 kilowatts solar electric propulsion and put it at the Earth-Moon L1 point, for example. And then you can send out, we've brought back 500 tons of asteroidal material. The OSIRIS-REx is costing $800 million to bring back 100 grams. So it's 1 million times more cost effective, with the slight catch that this is at the L1 point. So you have to spend a little to get out there. But that's great, because now you have a place for the astronauts to go and a reason for them to go there, because with this rock you can do tremendous science. I'm going to organize a conference on that next year. But you can also practice techniques of handling a very uncooperative body like this, with sharp edges, not like docking with the space station. It's going to be quite different. Grabbing a hold of a loose rubble pile like this is really difficult. It just comes away in your hand. What do? There's a lot of techniques there. And then learning how to process asteroid material into useful and valuable resources is something else that will be much better done with having astronauts at your asteroid. Because astronauts can solve problems in real time. They can dig the pebble out of the mining machine that would otherwise be non-functional. So it's a great place for astronauts to go and be very, very useful. And that's to give you the scale of what we're talking about. It's not a very big asteroid. So I like to use this analogy of the American West. This is a huge frontier. There was never any doubt this is a unpolitical statement. There was never any doubt in the American mind that we would be expanding the country out to the coast there, which we kept secret for a while. But after the Louisiana Purchase, we had this huge amount of territory. It wasn't solidly ours, as you may think. There were many competing interests, but it gave us a reason to go there. It was a many-decade program, a 5-decade program of exploration and development, and it was subsidized by the government, very much so. But the government didn't own it. The government was developing it and buying down the risk for the pioneers. Those guys setting out in those Conestoga wagons, they were not crazy. And they knew they had a reasonable chance of making it out there because the government had done a lot of work to map out the territory and make it safe. So if you take this goal for NASA, enabling the commercial development of space resources, it will be the same thing for space as we had in the West, the same role for government. It is not to do the job, but to enable others to do the job. And this is where now $13 billion of exploration money no longer seems like a throwaway. It becomes an investment, and that means we could easily imagine doubling that budget for the truly explorational work. How long is it going to take? There's the 1804 map from Lewis and Clark of the West, and 2 generations later, the West was part of the US economy. The Transcontinental Railroad was completed, and I think the same 2-generational timescale is right for this commercialization if we do it right. And so you guys are in the most exciting generation of that, the first pioneers going out to do that, and I hope that's what you will do. Thank you.
Okay, simple. We're gonna go here. Any questions? All right, good. I need that back phone. While I'm waiting for a slide, we're going to go to the moon. We're going to go someplace. Yeah, as you said, I'm Paul Graham, Kepler Shipyards, which is we're using Open Luna's tech to make, well, commercializing it, and Open Luna, where we're going to build an outpost on the moon. As far as why the moon, or why elsewhere, or why not elsewhere, I'm going to go back to his analogy. Think of the American frontier. Government kind of surveyed the outer edges. Government kind of pointed out where this is where you can go. They paid for the really expensive stuff and cleared some of the risk. And then private industry filled in behind it. Private industry came back in and laid down the infrastructure, laid down the railroads, set the paths, built the stores, made the infrastructure happen. It wasn't government, that was private industry. So we're doing the same thing now. We'll let government go and establish the frontier, and of course we'll be pushing them hard because they never establish it fast enough. And then we go back behind them, we being commercial, and back to them. Lay down the infrastructure, make all the money that government left behind. And that's what we're doing. And so to answer my question, why moon? Because we just simply can't afford to go further yet. Today, we'll go to the moon. Tomorrow, someplace else. Why? Well, I'm going to use my favorite line, because we need the ultimate offsite backup. And we can talk about how there's all the riches there is out there, and there are, more than any of us could ever spend in our entire progeny's lifetimes. But we need to get off there first and make someplace safe. So, what I'm going to give you is where on the moon. Now, this is a presentation that Dr. Phil Stuke presented to us as far as why we should go to the south pole of the moon back in 2009. Now, you may know Dr. Phil Stuke or not. He's the cartographer who found Lunokhod 2. It launched and vaporized and no one knew where it went. Well, when LRO went up, he found it. He found the debris of it. And so this is his presentation of why we should go where. Because I'm not a huge fan of really monstrous PowerPoints anyways. So here is a picture of the South Pole moon. LRO data, the LRO pictures in Cayuga, the radar typography. and here is where the sun is. Because what do we need? I mean, there's really three things we need to be on the moon. We need power, that's obvious. We want water, because we can use water to drink, fuel, oxygen. There's lots of good reasons to have water. And we want something interesting. We can just go for the sake of going, and you can ask all the geologists what they thought about Apollo 11. It wasn't, I mean, it was cool, but it wasn't that interesting, because there was nothing there that was exciting. Well, we want to go someplace exciting. Give us a reason to go there rather than just consume power and water. So, this is our power. The black areas, cold wells, there's probably water there. We've got a really solid indication there's water in those locations. So we want someplace that's right where the two meet. Here we have our illumination, and we have our water. Here's the two maps laid on top of each other. Now they're a little bit off scale, but you can see the dark areas are basically in perpetual darkness. The lighter areas are in some larger scale of light, 6 months or longer. What we're looking at is some place where we have good illumination and good darkness right beside each other. Someplace like, right there. I think everyone recognizes, anyone who's familiar with lunar exploration recognizes the name Shackleton. That's the crater to go to, it seems like. There's a good reason for it. Because you have water, you have cold wells, and you have light all the time. What Phil discovered was two really cool things, is between these two spots, 12 kilometers apart, you have 100% light coverage, 98% light coverage. I think it's 2 days out of the year that you're without light. That's pretty doable. These are the specific locations, and he's not showing Melpart Mountain. What Melpart Mountain is a really neat spot just off to the side. Melpart Mountain has 80% light coverage and complete visibility of Earth and all of our landing sites. So it's a really great radio relay, stop-off point, wherever. So I'll get to why there or what there in a second. So there's Melpart Mountain, and as you see, it's 80% illumination. And it's not that far away. That's a really, really quick radio hop or laser hop. It's just not that far away. It gives us near-term communications until you can get the satellite infrastructure going, right? So, if you look at these two, A has, and I don't know why it didn't end up here, our site A, the one right by the crater, has illumination for, its longest gap is 12 days. The longest gap without illumination. I think the total gap throughout a year is 30 days. It's not bad. An 8-day stretch and a 12-day stretch, 6 months apart from each other, and then a day here and there. That's there. The other spot has 6 months between the two. You've got near 100% coverage. 12 kilometers is not a long way to lay a microwave beam or a cable. It's not far at all. So we've got power pretty much covered with those two spots. And you can see really well, we've got a really nice cold wall there and a really nice cold wall there. So now we've got water, we've got power. I think that's where we're going to go. Here's the map if you want to actually look at the illumination, see which is which. You can see where the spot in B has some big chunks of dark time. But in A, that one right there is the biggest hit, and it's 12 days long. So that's pretty doable. You can store it 12 days. When you consider you're going to bury a structure, you've got some, you can save some heat in the ground. So, and there's Melpart Mountain. We've got, can pretty much cover all of our daylight, all of our communications there. And note that all of the light regions, none of them intersect. They're all different. So we've got light coverage basically all the time. And that's why I say we're going to go to the South Pole Moon. Really quick for the other part.
Okay, I'm going to be, hi, I'm Ken Murphy, I'm president of the Moon Society, and we can toss around a beach ball, a lunar beach ball. No, you just throw that up there. Okay, so I'm going to be introducing you guys to cislunar space, and I'm calling this for the 3D generation for a very specific reason. Throughout history, humanity has had a two-dimensional perspective because it ties to land. It's all about this land and that land and that land, and this one has resources, so you know what, I'm taking this. We need to start thinking 3 dimensions. The United Nations did a report a couple years ago. They said we needed 2.5 Earths worth of resources for everyone in the world to live at our standard of living. 2.5 planets worth of resources to get that. Well, guess what? There's 8 or 9 planets up there, and then lots and lots of small bodies. So think 3-dimensional. Also think up instead of just across and forward. One thing, Earth is Switzerland. We are in the bottom of a deep, deep gravity well. This is Leo. This is Geo. When they say when you're Leo, you're halfway to anywhere, it's because you're halfway up out of this gravity well. So, considering that Earth is Switzerland, what do you export from Switzerland? High value added goods. Cuckoo clocks. Excellent chocolate. Finance that you can't get anywhere else in the world. High value added goods. That's what we're going to be exporting from Earth. Right now we export everything. High value added, low value added, medium value added. Everything is coming from here. We need to change that equation so that we're tapping resources out here to use out here and not having to ship everything up out of the gravity well. This is just a side view. Kind of interestingly, this SLEO, that's sea level Earth orbit, if you were to have a satellite at sea level, that's how much energy you have to impart to it. It's not a good place for it to be because we'd all be jumping around as the satellites came through. This is the vertical component. This is why space elevators are so exciting, because that's your space elevator energy, right there. This part, that's to get you going this way so that you're falling as fast as the horizon is. This is the vertical component. And then of course you have another leap out to GEO. You've got your L1s here. Now, if you're going to be searching for zombie sats in GEO, do you want to be doing that from LEO? Or do you want to be doing that from L1? To and from. It's cheaper to go from L1 to GEO and back than it is to go from LEO to GEO. So we need to get up out of this gravity well. I wrote an article for the Space Review back in February, I think, and Jeff, thank you for publishing that. I do appreciate it. This was a graphic I put together to describe how it's not just about the moon. There is an entire sphere of economic activity that goes on between here and the moon already. When we look at LEO, these are hard to see, but we've got the ISS up there. People have been talking about free flyer platforms for 25 years at least. Bigelow balloons, there are 2 test balloons up there right now, but he's looking to put more of those up there. And of course, one of the key next steps is fuel depots. Because just like you've got a gas station in your neighborhood, we need to put gas stations in some of the other neighborhoods between the Earth and the moon. Out at GEO, you've got your ComSats, your broadcast sats, problems with zombie sats. We want to look at larger things like broadcast platforms, so if you have Dish or DirecTV, it'll actually punch through the rain. And then Dr. Elvis doesn't agree with it, but solar power satellites eventually. At the L1 point, that can serve as a comm link to the moon, a transit node to other destinations on the interplanetary superhighways, Mars, asteroids, and so forth. Again, a place for free flyer platforms, fuel depots, and a staging platform for going to other destinations. And then of course on the moon itself, oxygen, because one of the thumbnails is down here in LEO. To get a ton on the moon, you need 5 tons in LEO. 5 tons in LEO gives you 1 ton on the moon. Why is that? Because the other 4 is your propellant. You're about 75–80% propellant. What is 7/8 of that propellant? It's oxygen. How value added is oxygen? Not much, but we're shipping it all up out of the gravity well. We need to start sourcing it from other locations. Dr. Arthur C. Clarke wrote a paper back in the 50s talking about the economics of lunar oxygen as a propellant in low Earth orbit. That's not a new phenomenon. And studies have shown again and again, this is going to be the first thing that could make you money if you're doing economic activity in cislunar space. You've also got the metals on the moon, the rare earth elements that we need for things like cell phones and iPads and stuff like that. solar, wind, and planet elements, which are your light gases, which also give us a record of the sun's activity over 4 billion years. You know, people talk about global warming, global cooling. We really don't understand the sun as well as we'd like to. We have a record of what it's been doing for the last 4 billion years on the moon in the form of the solar, wind, and planet elements. We can go study that. We can get a much better sense of the life of our moon, of our sun. There's other science missions to do as well, like crater counting and dating. You can get solar power satellite components from the moon, basic low value added components like structural elements, solar panels, that sort of thing, and eventually exotic goods. So from the map that I had published, Le Monde Diplomatique did an article back in August, and they took my map and actually made it prettier. But you know the French, they're very artistic and lovely people. So they basically took my map and redid it. Geosynchronous orbit, blah, 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 future home solar power satellites. I talked about zombie sats. It is a problem. Because of the way orbital mechanics works, where you have higher density masses, the orbit gets pulled in. When you have lower density areas, lower gravity areas, the orbit kind of pushes out a little bit. Centrifugal force will then move satellites into those outbows where there's low gravity density. Here you can see where India slid up into the Himalayas, gouged out the Indian Ocean. The real problem though is at 160 degrees west. Why? This is a lot more active geoband than over India. So there's a lot of debris here, and this little light blue area is giving us a bowing out where the centrifugal force is starting to accumulate. And if I remember correctly, it's like 150 dead satellites out there right now. Space-based solar power, Dr. Ellis doesn't agree with it. I don't agree with it if we're lifting it from the Earth's surface. If you're building everything from the Earth, this is stupid. If you actually have a space economy and you can decide, we'll take the low value added components sourced from the cheap places, the high value added components sourced from the expensive places, you can start looking at this. And again, every one of us remembers the BP spill, so we can start taking that out. Another thing we can do, if we go to L1, is use the interplanetary superhighways and actually set up a network of probes throughout the solar system that are periodically returning home for service, just like the Hubble. And then we send it back out on station using these interplanetary superhighways. And instead of one Jupiter mission every 20 years, instead we've got stuff that's out there all the time collecting data. On the moon, I'm going to skip over that. This is a oblique view of the South Pole. That's Shackleton right there that Paul was just showing you. The Leibniz Mountain, or that's the Leibniz Plateau, also known as Malapert Mountain, that he was talking about. And you can see that it's very close to there. If you remember L cross, that hit Cabeus A, so L cross hit right over here. But the main thing we're going to do on the moon is our sandbox mode. If any of you guys play video games, you know what sandbox mode is. The moon is our sandbox mode. This is where we're going to learn how to live off planet. These are some of the goods that we can get from the moon, agricultural goods. This is work that was done back in the 70s. We've got scientists in the room. We know that you do experiments, you change one variable. There is a variable changed in here. The variable change is that this row has lunar regolith in the growing medium. This row does not. Now, of course, once they determined that regolith wasn't toxic, they stopped all these studies. And we only have a fixed amount of regolith, so we can't use that. But agricultural goods are a potential export from the moon. Alloys, anhydrous glass, glass that doesn't have water in it. Water permeates everything here on Earth. On the moon, glass is formed in a water-free environment, pretty much. How does that affect the optics? How does that affect the structural strength? We don't know that. There's energy, as Paul was talking about. Consumer goods, things like jewelry made out of moonstones. Helium-free, I agree, that's kind of a bagatelle. I'm not big on that. SWEs, again, you're going to be extracting these gases from the soil. They can have other applications, metal slag, and even shipping regolith. I mean, if you had a garden, wouldn't you maybe want to try some regolith in your garden? I'd be willing to sell that to you for a fair price. Now, your future. This is the hard part. This is a change, and this is the economics part of my talk. It's going to be very quick. It's not going to be fun, but it is very important. This is the change in employment levels by age group from 2007, kind of like right when the economic crisis hit. The only people that are getting jobs over the last 5 years are those over 55. This is the tail end of the baby boomers. This is your contingent, the 25 to 30 mainly. And then this is my group. We have not had a good couple of decades. Job additions since the end of the recession. Grays are 55 to 69. Of interest to you guys are the reds. These are jobs added in your age contingent from 20 to 24. And then from 25 to 54 are these guys. And then the greens are your teenagers, the guys that bag groceries and stuff. So again, you've got a very narrow window of opportunity until you're 24 to get a job. And after that, you're kind of hosed. So percentage change in median net worth. Again, these are the baby boomers. This is my generation, and then you guys are in this generation. We're not making progress. We need to change that. We need to change these from negative numbers to positive numbers. This is also a breakdown of the demographics at NASA. I figured this might be of interest to some of you guys. The dark blue are the silent gen. These are the guys, the greatest gen. They're over 70 years old, basically. The greens are the baby boomers. The reds are Gen X, my generation. And then the blues are where you guys are at. You can see that JSC and Marshall seem to be the two big locations for youngsters, with Kennedy and Goddard and Glenn at a secondary level. Ames kind of surprises me. I would expect to see more of you guys out there with Singularity and all that stuff. Where is the opportunity? That's the real question you should be asking yourselves. At NASA, it's going to be where the biggest gap is between the baby boomers and the Gen X, because there's 2 baby boomers for every Gen Xer in the world. There are not enough of these reds to fill all of these greens. They're just not there. And as you saw, we're not being given those jobs anyway. So you guys are gonna have a tough haul, but I would say that the biggest opportunity is where you see the biggest gaps between the baby boomers and the Gen X, because that's where they're gonna need you guys to help fill in. So I want to talk quickly about the Jobs Act, Jumpstart Business Startups. You guys know about Kickstarter and crowdfunding. It applies that model to equity raises. So if you're thinking entrepreneurial and you need $1 million or $2 and you got a good product and a good business, your ultra small business will be able to tap ultra small investors. You will be able to invest $2,000 each in the space company of your choice. That's something that we could not do previously. You had to invest in a mutual fund or something like that. So the business can raise $1 to $2 million, you can invest $2,000. Final rules are expected in early 2013, and then expect people to start going to town on that. The time is now. This is the key point. Nobody in the world does space the way the US does space. You've heard that from prior speakers and you can hear from future ones. We have an absolute commercial competitive advantage in this industry. Don't lose it. We've given up all our other advantages. Computers, gone. Biotechnology, all the cloning's being done elsewhere. Let's keep this industry for ourselves so that we can get the prosperity from that. And this is only one of the few where this is the case. We are where computers were in 1980. You guys weren't around for that. It was a very exciting time, computer-wise. And it's also the age of air shows for the space industry. The space industry needs to stop showing off to each other and start showing off to the public, just as it was noted with the airplanes. No one believed you could fly. And then an airplane came to the county show and took you up and flew. And it changed the mindset. People don't think we can do space. They think it's this weird esoteric thing. No, the industry is there, the commerce is there, we just need to show people instead of each other. So when you get out of this conference, share space with other people. And that is the end of my talk. Thank you. You're off the volleyball team.